Welcome to lecture 2.2 on the derivative at a point. We'll define what the term derivative means in just a little bit, but it is one of the main ideas of calculus, along with the limit and the integral. Chapters 2, 3, and 4 are all about derivatives. And just a little preview of what this is about. It's kind of the same idea as instantaneous rate of change from 2.1. The main difference with derivatives is that derivatives refer to any old function that isn't necessarily a positioned function, and it doesn't necessarily represent velocity. So we'll see exactly how that all works. But first, here's an example of a function. This is actual data that I found that somebody measured their own car using some engineering tools and software they had. And they found out that a Prius Prime was getting 80 miles per gallon at a speed of 40 miles per hour and 61 miles per gallon at a speed of 60 miles per hour. So yeah, find f of 60 minus f of 40, f of 60 minus f of 40 over 60 minus 40. So those two quantities. And remember that interpret means think about or write about what, I mean, if it's on a test, it means write about what these numbers mean in terms of the car, and include units as best you can. And then these A, B, C, and D represent different things with this graph over here. So this f of x is different from the f of x over here. I should have called them something different. Anyways, there's your warm-up problems. I will pause it, and after I unpause it, you will see the answers to these. So you're going to want to pause it right now because the answers will appear in 3, 2, 1, and here they are. So for warm-up 1 here, f of 60 means the velocity or the speed is 60, and f of 40 represents the efficiency when the velocity or the speed is 40. So that means doing 61 minus 80 miles per gallon, and that gives you a difference of negative 19 miles per gallon. And that number is negative because as the velocity increases here from 40 up to 60, the efficiency gets lower from 80 down to 61. So it's a decrease of negative 19 miles per gallon. The efficiency is 19 miles per gallon worse after increasing the speed that much. In B, same idea. The top is the same, negative 19 miles per gallon divided by 20 miles per hour. Now this is a weird sort of kind of number. You don't usually see numbers with this units. You've seen miles per gallon, you've seen miles per hour, but now this number represents negative 0.95 miles per gallon per miles per hour. Maybe we can write that as MPGPNPH is what this is. And let's think about what this means. What slope means in general is this is the rate that y changes as x increases by 1 is the way slope works. So for values of v between 40 miles per hour and 60 miles per hour, speeding up, increasing the speed, reduces efficiency by an average rate of change of 0.95 miles per gallon divided by miles per hour. And I didn't say negative here, although you could if you wanted. It wouldn't be wrong at all to say that's negative, but I already said reduces, so it's kind of a double negative, and it's not, that might actually mean increasing if depending on how you read it, but you know what I mean here. In other words, increasing speed by negative 1 miles per hour reduces efficiency by about 0.95 miles per gallon. So if you're going to have a graph of this function here, and you're going from, it's not going to be a very to scale graph, from 40 up to 60 miles per hour, and then you had the efficiency here. This would be going down at this rate. So if you plugged in 41 here, that's a change in V of 1, and the corresponding change in efficiency would be negative 0.95. It's a little bit small there, but that vertical distance would be negative 0.5 miles per gallon for every 1 unit increase in miles per hour. All right, looking at warm-up 2, the quantity A here, that represents the slope from 3 to 6, because again, this is like f of b minus f of a divided by b minus a. That 3 is 6 minus 3. So that gives you the slope of the thing between those 2 points, the vertical change divided by the horizontal change. And for a, it looks like that's 0 because between these 2 points, the vertical change is 0. So this is approximately 0 over 3. B is f of 8 minus f of 6 here. So f of 8 is less than f of 6. So when you subtract those, you're going to get a negative number. So this, oh Jesus. Anyways, f of 8 is less than f of 6, as you can see here. So this will come out to be something negative divided by 2, which is still negative. And f of 10.5 minus f of 8 gives you the slope here. That's a positive slope because you can see that you have a positive change in y and a positive change in x. So that's positive. And then let's look at d. That's the slope from here up to here. And this is positive also, but it's also steeper. You have a big change in y and a smaller change in x. So the slope comes out to be a big positive number. So that means, yeah, that the negative number is the least. 0 is in between the negative ones and the positive ones. And then you have the smaller positive one and the greater positive one. All right, here's our next topic. Barely made this fit in the screen. Whoops. Okay, so first, I just want to go over the main idea from section 2.1. I should have called this F here. That was a mistake. So if f of t is a position function at time t, then average velocity from t equals a to t equals a plus h is given by this thing. So it's the total change in the y coordinates divided by the change in the t coordinate in the bottom. And that's what we looked at then. And then also instantaneous velocity means just at that one point, you look at this interval, you make the interval between the t values smaller and smaller and smaller, and you look at the slope between those 2 points on the line, and that slope should be getting closer and closer to some number, which is equal to the slope of the line just at that point. So you take the limit as h approaches 0 of that average velocity there, and you get the instantaneous velocity. So we're going to do the same thing in 2.2, but we're looking at any function f of x, which isn't necessarily a position function. F of x could represent anything like efficiency of a car going x miles per hour, or any kind of function you can think of. And you can still look at the average rate of change, and average rate of change still represents the slope on the graph. It doesn't necessarily represent velocity here, but it represents the slope between these 2 points on the graph. And here's, a graph that demonstrates that. Accidentally pressed the wrong button. Here's the graph that demonstrates that. So you have your values of x here, like x equals a up to x equals a plus h. So h is the distance between them, and when you do f of a plus h minus f of a, you get that vertical distance, which is negative in this case. So the slope between these 2 points is a negative vertical distance divided by a positive horizontal distance, so you get a negative slope, and that's what the average rate of change means here. The derivative is the same idea as instantaneous velocity. It's what happens as you make this interval smaller. You take the limit of this average velocity as h approaches 0. So you get a smaller and smaller interval. These 2 points here, right here and right here, get closer together, and you see what happens to the slope. And I tried to draw this graph here, so I'm actually going to say what will happen. This thing is called the secant line, by the way, in green. That's a secant line. I'm going to erase it and try to get an idea for what happens when you just get the slope through that one point here. And we're going to ignore this other point. Okay, so just getting right through that one point. I tried to draw it so it's flat here. So if I try to draw the line that only goes through one point, well, that's not perfect, but just pretend it only goes through this one point here. And what is the slope of that new little green line I drew there? It looks like it's about 0. And this line that only touches it at one point is called a tangent line, and the slope of it is about 0. So that's what the derivative is here, which is kind of like instantaneous velocity of 0. So if this was velocity, what this would represent here, or I'm sorry, if this was a position function, let's just pretend for a second. If this is a position function, then the position is increasing, and then the position is increasing, so it's like moving forward or moving up or whatever you're measuring. And then after this point, the slope you can tell is downward, so its position is decreasing. So there's just a moment or an instant right at the top here where its instantaneous velocity is 0. So that's what the slope of that tangent line represents. And that's a difference between the derivative and an average rate of change of a function, is that the derivative is only talking about the slope of the curve at that one point, not between any 2 points. And the average rate of change is between 2 points, and it represents slope of secant line. Okay, for example 3, oh, and by the way, we use this, I didn't mention this, but we use a little apostrophe, and we say f prime of a is how you read this out loud. So this, if you're thinking this to yourself in your head, read this as f prime of 3. I don't know who turned that apostrophe into the word prime, but that's the way we read that out loud. So using Desmos.com, you can graph this and try to zoom in on this point, and looking at the grid, try to figure out what that slope is. And again, with these, don't kill yourself to do these examples. Try it. But don't spend an hour on one of these examples, because if you get stuck after, I don't know, 10 or 15 minutes, then you should definitely come back to the video and just see the solution and try to make sure you understand that. So you should pause it now, because the solutions will appear in 3, 2, 1. Here is my solution. I got about 1.25, and if you got something like, I don't know, anywhere between 1.1 and 1.4, you're close enough. And again, if you get, I'm not sure if I mentioned this, if you get this answer right and you feel like you understand it, feel free to fast forward through the explanation. You probably don't need to see me do the problem again and explain everything if you already feel good about it. That will save you a lot of time because it's probably boring watching somebody do a math problem that you've already done and gotten correct. So anyways, how did I get this? I'm actually using a little software called GeoGebra, which is the same idea as Desmos. It has a bunch of other features that Desmos doesn't have. And I'm using it because I think you can see the font a little bit bigger here. Anyways, so I'll show you what I graphed. Here's the function, natural log of x to the fourth. Let me zoom out again so you can see what the whole thing looks like. So the green curve is natural log of x to the fourth. And then I did a bunch of other fancy stuff you can ignore in order to set up this idea of the secant line, just because I think it's good to have a picture of this. So I set up an equation for a secant line between these 2 points. The blue one here is at 3 f of 3. And if you go to f of 3 plus h, you can end up over here. And so you can see how out here it looks like the secant line has a slope, something like this. It looks like, again, at h equals 0, the slope is undefined at 0 over 0. But if you have a small change in y over small change in x, when h is small, you can see what the derivative is approximately sort of equal to the slope of this thing. Now, so you could use this line, but you probably don't know how to set up that secant line. Or what you could do is just zoom in a whole bunch closer and closer to this point. And you can tell that here's 3. If h is 0.1, then the other point on the secant line is over here. And the closer you zoom in, the more the original function and the secant line look just like each other. And you can imagine that if this was really the tangent line, they'd be even closer. If the secant line was actually only touching it at this one point and not this other point over here, then these lines would be as close together as possible. And so I wanted to show you that any kind of smooth curve looks enough like a line when you zoom in that the tangent line is kind of a good approximation for how that curve behaves. But what the points I use were at 3 and then at 3.2. So f of 3 is about 4.4 here, or 4.39. F of 3.2 is about 4.65, halfway between these two. And you could use the secant line at that point, or you could use the points on the green curve itself. Anyways, the vertical change here is about 0.25. The horizontal change between these points is 0.2. So that's how I calculated that. Okay, this is the next example, which is example number pi. I'm doing this in a weird order because I just realized the last example I did, I think, was a little bit too hard for right in the beginning. So I'm going to put this one before it. So I'm actually recording this after example number 204. So that's why things might be kind of weird. Anyways, so this is a graph right here of f of x equals 1 over x. And first thing we're going to do is find f prime of 2 algebraically. I'll just write out what we mean by that here to show you the first step. Algebraically always means like actually find the limit as x approaches, not x, as h approaches 0. This is the definition of f prime of 2, of the derivative. As h approaches 0, f of 2 plus h minus f of 2 divided by h. So calculate that limit. And then b, using the graph, order these from least to greatest, and pause it now because the answers will appear in 3. And here are the answers. F prime of 2 is negative 1/4. And for part B, f prime of 0.5 is less than f prime of 1, which is less than f prime of 2. And those are those answers. Let's go over this real quick. So over here, I just plugged in 2 plus h and 2 into the function, and that's what those results are. And then to deal with these fractions within inside this fraction, I multiplied both the top and the bottom by 2 times 2 plus h on both the top and the bottom, so it doesn't change it. That's a way to clear out fractions within fractions. And when you distribute that into the top, everything cancels out, and you end up with a nice limit, kind of like the ones we did in chapter 1, and it ends up being negative 1/4. And over here, I tried, you don't have to do all of this. If you just got the answer, that's fine, but I want to explain it with some detail. So I tried to draw these tangent lines at these 3 points, and it looks like f prime of 0.5 is about negative 4, f prime of 1 is negative 1, about the slope of that thing, and then f prime of 2 is exactly negative 0.25, we already found. And so you might be saying, well, f prime of 0.5 should be greater because that's a steeper line, but it is steeper, that's true, at 0.5, but it's just a bigger negative number, and bigger negative numbers are always less than negative numbers close to 0, because lesser in math always just means to the left on a number line, and greater always means to the right. So that's how that works, and we'll do 1 or 2 more examples after this. Here is our next example, and I just gave up on numbering them correctly because I started with example 3. I never did examples 1 and 2. So I figured I might as well name them whatever I want. So we're doing example 204, and this one is about eucalyptus trees, which generally grow better with more water. Now, if you wanted to know how much more wood you can get from trees if you water them more, if you have like a eucalyptus tree farm or something, or if you're some kind of tree scientist, you may be interested in this rate of change of this function. I'll let you pause it and read it in a moment. I'll just say that part B here is hard to do it exactly using algebra. If you want to skip that one and just watch me do it, that's okay. But in any case, you should pause it because the solutions will appear in 3, 2, 1. Here are the solutions as promised. So for A, I just used h equals 0.01, and I did it in one step with a calculator. I'll show you how. I just took the formula for the meters cubed of wood and plugged in 100.01 for R, and then what you get when you plug in 100 for R, subtract that, divide by 0.01. Here's my calculator software. This looks basically the way it does on a TI-84 or TI-83 or whatever. And I did it all in one step, and let me explain why that's a good thing to do. Why it's a little trickier, but why is it worthwhile? It's worthwhile because what you're doing when you write out a big long formula like this is you're basically using the same skill that computer programmers use when they're programming. You're writing a big long expression in, it's not exactly a programming language, but it's mathematical symbols, which are basically the way programming languages work. And you have to make sure that you're matching up all your parentheses, which is a challenge when computer programming. And it has a lot of the same skills in common. So anyways, I like to do it all out in one step. And the nice thing about this is if you make a mistake, you can just go back on your calculator. You'd press second and then enter to go back to the previous entry and edit it. And you can do the same thing with any software you have. So anyways, I just plugged it all in and got 20.002. And remember, so what does that mean? Well, the numerator of this, the output of this function, represents the volume of wood that is produced in a year on a square kilometer of land. So that's the standard way they're measuring this volume of wood. And that's divided by 0.01. That 0.01 is like 0.01 extra centimeters of rainfall. And it comes out to 20 about. So that means, what does this rate of change mean? That wood production increases with respect to rainfall at a rate of about 20 meters cubed of wood for each increase in centimeter of rainfall. There's different ways to say the same thing. If you're not sure if your language is right here, feel free to show it to me. Everybody has trouble describing numbers like this because it's not, you don't usually see things like this in real life. Usually in real life you see rates of change in terms of like miles per gallon or miles per hour or dollars per hour, and meters cubed per centimeter. You're not used to describing that in words, so it's going to be a process. Just like I will get better at making videos, you're going to get better at writing things, so make sure to get some constructive criticism from me or somebody else for how to word things. Actually, section 2.4 is going to be all about interpreting things like this. So you'll get a lot of practice with it then. So that'll be later next week, later this week, next week, whenever. So for B, if you got part B and you did all these steps correctly, you get major extra credit points that you can give to yourself in your own mind. They're not real extra credit points, but this is a very hard problem because there's so many steps and so many places to make little mistakes. Anyways, I just plugged in 100 plus h into the function, and this is the v of 100 plus h part here. Squaring 100 plus h and multiplying it by 0.2 gives you this. And if these steps are confusing, maybe post in the comments of the video or in the discussion board about where you're getting mixed up on the step, and another student can answer to help you, or I can try to answer to help you. And anyways, after you square that out and you use the distributive property and you distribute the minus into all these different parts, a bunch of stuff cancels out, and that ends up coming out to the h's cancel out. You can reduce the fraction as long as h is not 0, and the limit is not concerned with h equals 0, so that's okay. And then you get 20 plus 2h, and the 2h gets closer to 0 as h gets closer to 0, so the limit is just 20. So yeah, give yourself a big pat on the back if you got that one correct. Or a gold star. Yay. Let's look at another one. All right, one more example to try here. This is example number 1,000,000. Here is a graph of g of x, and the graph of the tangent line there. Fill in the blanks. And I'll pause it here because the answers will appear in 3, 2, 1. Here are the answers. So g of 2 equals 5 because the point 2, 5 is on the graph of g of x. So yeah, when x is 2, g of 2 is 5, is that, and that's that. G prime of 2 means the slope of the tangent line at this point, and to calculate the slope of the tangent line, I did the change in y between these 2 points divided by the change in x, and we get negative 0.4. And now let's go on to some practice problems. Now again, these are ones that you should definitely do on your own. These are similar to things that you've just gone over, so you should be able to do these. And the answers will appear in 3, 2, 1. There's the answer to 1. Whoops, I'll pause it again to get you the answers to the rest. There they are, the rest of the answers. Okay, so for A, when we look at the average rate of change is larger between x equals 1 and x equals 3, that's because the graph is gradually getting less and less steep. So the slope between these 2 points, you can tell, is a little bit steeper than this slope. So that means a greater average rate of change. And for B, f of 5 is just the y coordinate that you get when x is 5, and f of 2 is the y coordinate that you get when x is 2, and you can tell it's a little bit higher here because it's going uphill from left to right. Your y coordinate when x equals 5 is a little bit greater. But then f prime of 1 is the slope of the tangent line here. I'm just going to make this really ugly. That's the slope. That's f prime of 1 is that slope. F prime of 4 is the slope over here, and that was weird. Well, the slope of the tangent line here, and you can tell that it's a little bit steeper at x equals 1 than it is at x equals 4. And for number 2 here, it should come out to negative 4. There's a bunch of different ways to do it. You could do it by plugging in values of x at x equals 0.5, and then slightly greater than 0.5, like 0.5001, and using the difference quotient. Or you could use the limit and do it algebraically, or do it with a graph. Either way, you should get something like negative 0.4. I'm sorry, negative 4.0 approximately. And anyways, I'll see you later in class.